Alright, in our next video we're going to take a look at some of the properties of limits. These properties of limits I've also typed up as a handout that are under in the Unit 2 section. If you have the limit, in the first one here, if we have the limit as x approaches a of a constant value, that c equals a constant value, remember that's just going to be a horizontal line at y equals c. So no matter what the a value is, that limit's always going to be c. If we have the limit as x approaches a of only x, then that's going to be a. If you have the limit as x approaches a of a polynomial function like f of x plus or minus g of x, then that's going to be f of a plus or minus g of a. If you have the limit as x approaches a of two functions multiplied together, f of x times g of x, then that's going to be f of a times g of a. If you have a division problem, you can take the limit of each one of them individually and then divide it out. So if we have the limit as x approaches a of f of x divided by g of x, provided a is not a restriction on the domain of this rational function, you can take the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. If you have a constant out in front of a function, like the limit as x approaches a of some c value times f of x, you can pull that c value out front. So you can write it as c times the limit as x approaches a of f of x. If you have the limit as x approaches a of x to the nth power, that's simply a to the nth power. And if you have the limit as x approaches a of some function f of x raised to the nth power, then what I can do is I can find the limit first and then raise that to the nth power. So I can go the limit as x approaches a of f of x and then raise that all to the nth power. Couple more. If we have a polynomial function, the limit as x approaches a of p of x equals p of a. P represents a polynomial function. If we have a quotient, a rational function, the limit as x approaches a of some quotient q of x equals q of a. The limit as x approaches a of the nth root of x is equal to the nth root of a. And we can also write that as a function as well. So if we have something like the limit as x approaches a of the nth root of f of x, what you can do is you can find the limit of the function underneath and then take the nth root of that. So we can go the nth root of the limit as x approaches a of f of x. Sometimes easier to find the limit first and then work from there. We also have a very interesting theorem, which I'm not going to use at this point, but I'll be using this later on in the class to prove some of the trig derivatives down the road. It's called the sandwich theorem. And the sandwich theorem is fairly understandable, and like intuitively it's understandable, but how you use it sometimes gets to be a little bit tricky. And what this says is that if you have a function f of x that is less than or equal to a second function h of x, which is less than or equal to g of x for all values of x in the domain, and if the limit as x approaches a of f of x equals L, and that's the same for g of x as x approaches that same a value. Basically what we're saying is that as x converges to a, the value on the bottom, f of x, and the value on the top, g of x, are going to converge to the same number. So then our conclusion would be the limit as x approaches a of h of x is going to be L by the sandwich theorem, because the ones on either side of it are converging to L, then h has to converge from L. And what we do is we use this theorem to prove that certain relationships are true, even though they might be a restriction on the domain of h, because the lower limit and upper limit are the same, then we can say that h goes to the same particular value. I'm not going to do an example of sandwich theorem here first, but I will get there in just a few moments. But one of the things I'm going to do with you here is I give you a couple problems, or give you a problem or two where you have to evaluate the limit as x approaches a particular number, and we're going to do like long division, or you have to factor by grouping, or you can use synthetic division. In this particular case, what I could do is I could do the factor by grouping, and I just wanted to kind of review that with you. Obviously 2 is a restriction on the domain, so since 2 is a restriction on the domain, I can't just plug in 2. So then the second thing is I have to try to remove the restriction at 2. And oftentimes what we try to do is we try to go ahead and factor. And remember that when you have 4 terms like we do in our numerator, we want to factor by grouping. So what they have in common is a 2x squared. So I'm going to rewrite this as the limit as x approaches 2 of 2x squared times x minus 2. And then I'm going to write it as plus 1 times x minus 2. That second set, the x minus 2 right there at the end, they don't have anything in common. So I'm going to factor out a 1. I write the 1 there only because when I do my grouping in a minute, I'm going to group the 2x squared with the plus 1. And so that's why I write it there. If you don't want to, it's fine. No big deal. The x minus 2 is still on the bottom. Now I factor by grouping. In the numerator, I have an x minus 2 in common, so I can rewrite the numerator this way. The limit as x approaches 2 of 2x squared plus 1 times x minus 2 over x minus 2. Now I've just removed that restriction. The x minus 2's will cancel, and I can let x be 2, and this limit is 9. So again tonight you're going to be working with more and more properties, or today you're going to be working with more and more properties, and with those properties you're just going to have lots of factoring, you're going to have all kinds of different stuff that you have to do. All right, I think you're ready to do the next assignment.